Here we are seeing another example for the JFormat instruction. We have the following information. So we have two labels here and there, and each of them, we have the address of those labels. And this is a code that we have. So here is the label that we have the address, and we have a jumping structure that is jumping to there, and we have the address for there as well. So what the question is asking is, we want to know the content of the word at this memory address. And basically here, this one. So first of all, what does it mean that we want the content of a word? So if this is our memory table, so this is the address, and this is content. So we have at some location, so for example, here we have 400,104, and it has some content. And then we have some other locations in the memory, and somewhere else we have 400,41C. So that is here, and that's there, the label. And this one has some content also. So what are these contents? So obviously, these are part of our code or text section, and these contents are actually representing instructions. So they are assembled instructions. So that's the given. So when this is asking to get the content for that location on the memory, and we know that this is the address for here, so that basically what is asking is to assemble this code. So that's basically the question. It's the same thing. So showing the content of this memory means we want to know what is here on this location, and that's of course the assembled version of this instruction, because that is this address. Okay, so first we have to know what is the jump. So we are going to look at the table, and let's go to the next slide. So we see that this is a jump instruction, and as we've seen before, we have 26i, so that's 26 bits for the I value, and we have 6 bits that is basically the opcode or identifier for the instruction. So we can think of it as an ID for the instruction or an instruction number. So this is how the processor knows what instruction we are dealing with. So that's a jump instruction, and this is the code for it. So 000010. And then the rest of it is going to be the I. Okay, so if we go back now, and if we look at this, so basically the answer is here. I'm gonna actually do it again. So I'll go through it basically. So the code that we saw on the table was 4 zeros and 1 0. So that was the opcode. So, and then we have an I. So we see in the previous slide how the I is calculated. We said we have 4 bits from current instruction. And that's basically the location for the current instruction, right? The memory address of the current instruction. And then we have 26 bits for the I. And then we have 2 bits, it's 0. So 0 and 0. So basically that's what we have. So before I continue, I want to write this in the full 8-digit format. So I'm going to change this. So I want to put 4 digits and then 4 digits. So we have here 0, 0, 4, 0, 0, 1, 0, 4. That's for here, and there we have 0, 0, 4, 0, 0, 4, 1, C. So if I have this jump from here, from this location, I want to jump there. So this last digit, here, it has to match. If it's not, we cannot do that. Basically, this jump not going to work because the way that we are constructing back the address is going to be basically this 4 bits is coming from here. So that's the target address that you're jumping. So this 4 bit is coming from this line. So it has to match. So that's a good news because both of them are 0. So I is going to come from here. So the rest of that. So I'm just going to put that down here. We have 0, 4, 0, and then 0, 4, 1, C. So if I convert this one to binary, I'm gonna get 0, 0, 0. 4 is going to be 0, 1, 0, 0. Again, we have a 0. So maybe I put, and then we have another 0. So 0, 0, 0, 0. I'm gonna write down here also, this is 0, 4, 0, 0. Again, we have 4. So that's 0, 1, 0, 0. And then we have a 1, which is 0, 0, 0, 1, and a C. C is a 12. So that's 1, 1, 0, 0. Okay. So this is our, basically the rest of the address that we have. So how am I going to get the I? We said the I was only this 26 bits in the middle. So this one, we had a 0 here before, and I already dropped that. So I didn't even write that. So the I is going to be all that except these last 2 bits, because that's going to be 26. So 1, 2, 3, 4, 5, 6. 6 times 4, that is 24, plus 2 here. So that's totally 26 bits. So that is going to be my I. And this 2 is discarded here. So this I goes there, basically. This 2 is discarded, this last 2. And here we had another 4, that was this one, and that is also discarded. And when the processor is basically contracting this address back, when it's going to look at this address, it's going to add these 4 zeros from here, from the current line, and it's going to add the 2 zeros, because always any address that is word aligned is going to have these 2 zeros. So basically, this is the answer. So I just have to basically write that here, and then, so this is 4, 0, 0, 1, 0, 0, 0, 1, 0, 0, and 1, 1, 0, 0. And if you want to write it in hex, sorry, this is just 1, 1. if you want to, let me change back to red. If you want to write this in hex, you just have to do a different grouping. So you're gonna take this 4, and then this 4, then this 4, and then finally that. So that is going to be your instruction. So then we can convert this one and put it instead of this. So that is 0, and basically you just do a hex value for that. So 0, 8, 0, or 1. You get the idea. 1, 0, 0, 0. I think all zeros, and then 1, 1, 2, 3. Actually, 2 zeros. Doesn't matter. You just have to convert it. Here is 0, 0, 1, 0, and this is going to be 7. So something like that. And that is going to be your basically the final answer of the content that is here. So just to recap very quickly, we had basically this code here. We have 2 labels. So here represent the current line of the execution or current line of the code. There is somewhere that we are jumping, and the question is asking what is the content of board at this address, and that's same as here. So what we are doing, we are just saying that since it's asking for the content of this location, that is the same thing as asking for us to assemble this, because the content of this location is going to be the assembled version of this code. And we assemble that. We look up the table, J, we had the opcode, and then we have 26-bit for the label. And that 26-bit is coming from the address of this there. We just have to discard 4 bits from that, from the most significance, and 2 bits from least significance. And that's how we get this I. And then it's just like if you want to convert it to hex, you can do that. The last thing here on this slide is actually very important. So what if basically the location that you want to jump is larger than this? So for example, if your here was that number, but then there here you had 0, 1, or sorry, you had 1. So because we said this last 4 bit comes from the current address. So what if this basically this most significant bits that you have is different than where you want to go? And basically it is not possible to do that directly with jump instruction. So that's the case that there is a limitation. So what you have to do instead, if you have to jump that far, you are going to use kind of same thing I've seen in the previous chapter when we are constructing a 32-bit number. So you do build this using the load upper immediate. So basically you construct your full address in a register, and then you are using a jump register, and you are giving some register to it, and then you can jump to that location. So we've seen the example of this in previous maybe 3 or 4 weeks ago. Okay. So here we briefly looked at this. We have few of other instructions that are basically J format. So these are, we saw jump and link. We have one more that is jump register, and that is very special because it has all zeros except that one register that you are going to pass to it. And that's basically another jump. So if you're assembling something like that, you have to basically come back to this table and look at this pattern. Another instruction that we have that is technically, I would say technically is not a J format, is a system call. And that has the opcode of basically zeros, and only it has 2 bits set. So that's another kind of special instruction.